In this video, we will begin our discussion of electrophilic addition reactions to nonpolar pi bonds. In other words, alkenes and alkynes. We will explain why alkenes often react as nucleophiles or electron-rich species. We will predict the products of addition reactions to alkenes, considering all the factors we've discussed in the past: regiochemistry, which site on the molecule reacts, and stereochemistry, how in space does it react when appropriate. We will provide reagents necessary to effect addition reactions to alkenes. We'll propose complete curved arrow mechanisms, and yay, it's back, identify carbocation rearrangements. Let's review this slide from the FMO lecture. The highest energy filled molecular orbital for an alkene is pi cc. The lowest energy empty molecular orbital for an alkene is pi star cc. For hydrochloric acid, the highest energy filled orbital are the non-bonding electrons on chlorine, and then the lowest energy empty orbital is sigma star HCl. Now, to determine which of these species will act as the nucleophile, the electron-rich species, and which will act as the electrophile, the electron-poor species, we can look at clues, but neither of these species are charged, so there aren't very many clues here. So what we can do is think about which has a good donor and good acceptor. Look at our lists of good donors and good acceptors, and we can see what? Yes, that the alkene has a good donor, pi cc, and the hydrochloric acid has a good acceptor, sigma star hx. So these two orbitals will react. The nucleophile will be the alkene, and the electrophile, the species that accepts electrons, is hydrochloric acid. For this particular problem, we were tasked to draw the single elementary step, just the first one, that might occur between these two species. Now, either carbon makes a bond to hydrogen because those two carbons are exactly the same. So we'll just choose the carbon on the left to make the bond to hydrogen. That leaves the carbon on the right with just the two bonds to hydrogen that it already had. And so there's a positive formal charge on that carbon. Make sure that you know where each pair of electrons went. So the electrons in the pi bond, pi cc, they made the bond to hydrogen. And when you filled up sigma star, you broke sigma, those electrons went to chloride. A couple of points here. So a sigma bond was made, broke sigma HCl. And then this carbocation carbon is sp2 hybridized. It has an empty p orbital. And anything else significant about it? Yes, it is electron poor and will react with electron-rich species. Okay, that's to come. Good, I hope that this review was helpful, jogged your memory here. That is an example of an electrophilic addition reaction, or electrophilic addition elementary step. So let's pause and generalize the pattern represented by this elementary step. How will you recognize it? Well, there's an alkene that reacts with some electrophile, some electron-poor species. Okay, and if we want to think about how do you know it's electron-poor, well, this HCl bond is polarized, and so there is a delta plus on hydrogen. And when the electrophilic addition occurs, as we showed on the previous slide, a carbocation is generated. And this is electron poor, it's high energy, and you know already that it will definitely continue reacting. So today we finally get to learn what will happen to that carbocation after the electrophilic addition. It will continue reacting, and today we'll talk about how it continues reacting. Yes, awesome. To summarize, the significant orbitals for an alkene for a double bond are pi and pi star. Pi is the donor orbital, the possible donor orbital, the highest energy filled pair of electrons, and pi star represents the lowest energy empty orbital, which may accept electrons, but for now we're unaware of how it or if it does that. But we are aware, we've said several times, that pi cc, this pi orbital, it is a good donor. And so we predict that alkenes will react as nucleophiles, as electron-rich species, same thing, and they donate the pi electrons. Okay. So given that, let's predict the product of the following reaction. If you'd like, pause and do that. Well, we can see there's an alkene. We also have hydrochloric acid, call it its HX. It's a strong acid. So the first step is to protonate something. Strong acid, protonate something. We may recognize that these are the same functional groups, the same reagents, essentially, that we examined for this electrophilic addition reaction to start the lecture. So you might just apply the pattern, and that's perfectly fine. The alkene donates its pi electrons to sigma star HCl. This generates a new carbon-hydrogen bond. And that bond can be made between either of these carbons. I will choose to make it at carbon 1, but that choice is arbitrary. Now, when those electrons in the pi bond are used to make this carbon-hydrogen bond, that will leave the other carbon, which we're calling carbon 2, with an unfilled octet. I'm going to go ahead and I'm going to draw this intermediate out in a 3D conformation so we can take a nice look at it. So there's carbon 1. It made its bonds to hydrogen, its new bond to hydrogen. And then we'll take a look at carbon 2. Carbon 2 is a carbocation. So it has trigonal planar electron geometry. And we can see that p orbital now, this empty p orbital, which can accept electrons. So we know that carbocations are electron poor. They'll act as electrophiles. We need to look for a nucleophile in solution. And our only choice, the only choice, is chloride. Chloride can donate its non-bonding pair of electrons. And chloride, of course, was generated when we reacted with HCl. So we generated chloride there. Let's take this chloride, move it over here. So chloride can donate its non-bonding pair of electrons to the empty p orbital on carbon. What is the name of this step? Coordination. Now, coordination can happen either to the top face or to the bottom face of that p orbital. I've shown it to the top. And it doesn't really matter for this example which face it bonds to, because you're getting an achiral product anyways. And so we have this alkyl halide product. So finally, the mystery is solved. After the electrophilic addition step, there's a coordination step to relieve that stress on the molecule, which is that positive formal charge on the carbocation carbon. generate an alkyl halide product. Now, overall, we can see that 2 new bonds were formed by these 2 elementary steps. HCl has been added across the 2 carbons of the alkene. Let's apply this pattern to another example. Please pause and predict the product of this reaction. Then provide a complete curved arrow mechanism that explains its formation. We observe an alkene and we observe HX. So last time I told you, oh, protonate something. Yes, that will be what happens in the mechanism. But now you know with an alkene and HX, you will add HX across the 2 carbons of the alkene. So there they are. We've added them across the 2 carbons of the alkene. Of course, carbon 1 had that implied hydrogen there. Okay. So HBr. Excellent. To generate an alkyl halide product. Oh, and I shouldn't put X. I should put bromine, Br, since that's the actual halogen we're adding here. Now this is going to proceed, this reaction proceeds by 2 steps. Electrophilic addition followed by coordination. So let's do that. Let's apply that pattern. So the alkene donates its pi CC electrons to HBr. 1 carbon is going to make a bond with the hydrogen atom, and the other carbon will become a carbocation. Now, those 2 carbons are exactly the same. So you can just choose which carbon you want to protonate. I will protonate carbon 1 because that is what I did in the product. But again, they're the same. The numbering is just to help you keep track of what's going on here. So now we have a secondary carbocation. I've just put that implied hydrogen so that you can tell what's going on. This is an electron poor species. It's an electrophile. Its acceptor orbital is that empty p orbital on carbon. Bromide was generated in this step when the HBr bond was broken, and so bromide will coordinate to that carbocation, relieve that positive formal charge, give carbon a complete octet, and form the alkyl bromide product. Excellent. So electrophilic addition followed by coordination. You might notice that electrophilic addition and elimination reactions are the reverse of one another. So today we're talking about the alkene, HX adding to it to form the alkyl halide product. But in previous lectures, you've learned about eliminating HX to form alkenes. So today we're talking about the addition. It's the reverse reaction. Let's think about what might be favored thermodynamically. So you can see that we're making sigma bonds. So we're going to break the pi bond going from alkene to alkyl halide. So the pi bond is broken and make 2 sigma bonds. So we're making this sigma bond and this sigma bond. We break the pi bond, and then with this HX bond is broken as well. While sigma bonds are stronger, so the addition is stronger than pi bonds. So the addition is favored by delta H. Sigma bonds are stronger than pi bonds. But the elimination is favored by delta S because we're going from 1 thing to 2 things. Okay. So what is the point of this slide? To show you that these 2 processes are the reverse of one another, and just to point out that one is favored by delta H, one is favored by delta S, and unless I say otherwise, you can just use the appropriate conditions that you know to make whichever direction occur that you would like. So let's try again, staying on this theme of electrophilic additions to alkenes. So can you predict the product of this reaction? Please give it a shot. When an alkene is treated with HX, the hydrogen and the halogen add across the two carbons of the alkene. Now, this alkene is asymmetric. And so this time it will make a difference to which carbon each of these atoms make. What I mean is that the two possible products here are constitutional isomers of one another. Hydrogen could add to C1 and bromine to C2, or hydrogen could add to C2 and bromine to C1. However, only one of these products is formed. So there's a tertiary alkyl halide possible and a primary alkyl halide possible. We're going to have our discussion. We're going to refer to these molecules in terms of the halogen. And it turns out that the tertiary alkyl halide, the more substituted product here in regards to the halogen, so the more substituted product is observed. This is the only observed product of this reaction. Both of those products were possible, but only one is observed. Now let's think about what that tells us about the mechanism of this reaction, which is HX addition to alkenes. So far we know it proceeds by two elementary steps, electrophilic addition and then coordination. If we think about the mechanism necessary to form both of these products, the first step will be an electrophilic addition, where we have the pi CC electrons attacking sigma star HBr. That breaks the sigma HBr bond. If C1 makes a bond to hydrogen, that would lead to this intermediate. Okay, C1 makes a bond to hydrogen. If C2 made the bond to hydrogen, that would lead to this intermediate. Let's describe those intermediates. This one, where C1 has made the CH bond, is a tertiary carbocation. The other possibility is a primary carbocation. The primary carbocation would react with bromide in a coordination step to form the primary alkyl halide. The tertiary carbocation would react with bromide in a coordination step to form the tertiary alkyl halide. Now we know that the only observed product is the tertiary alkyl halide, the more stable one, because I told you that. And I'm not making it up. So what does that tell us? It tells us that the only carbocation formed is the tertiary carbocation. Is that surprising to you? No, of course not. Tertiary carbocations are more stable than primary carbocations. So this reaction proceeds via the more stable intermediate, which is the tertiary carbocation. What do you think that we will do next? Yes. Oh, well, first we're going to formulate a rule, and then we're going to draw a reaction coordinate diagram. I can't wait. A chemist named Markovnikov noticed that when asymmetric alkenes were treated with HX, the more substituted product was observed, not the less substituted product. So he called the observed product, obviously, the Markovnikov product. Name it after yourself. And the product that was not observed, the anti-Markovnikov product. It contradicts Markovnikov's rule, which is that the more substituted alkyl halide is observed when HX is added to alkenes. So that is Markovnikov's rule. It is a rule. It is not a law, all right? It is really just a description of an observation that someone named after themselves. So the more substituted carbon of the alkene, the tertiary carbon, bonds to X, or if you will, the more substituted product is observed. Now that a more general way of stating Markovnikov's rule is written out below. You're going to love this or you're going to hate this, but it is what it is. So we're going to see in a minute that there are other types of atoms that can add to the two carbons of an alkene. It's not just H and X. It's not just acids. So when two atoms, any two atoms, we'll call them X and Y, add across the two carbons of an alkene, we will see that Markovnikov's rule is typically behaved. So if X is more electronegative than Y, then just like X is more electronegative than H, okay, then X, the more electronegative atom, will add to the more substituted carbon. Sound good? All right, and now, of course, why is this? So why did Markovnikov make this observation? Because of the laws of the universe, because these reactions proceed via carbocations, and the lowest energy carbocation is observed, period. Let's go ahead and look at the reaction coordinate diagram for this. So first, I've drawn out the two mechanisms. The mechanism on the left is to make the Markovnikov product, the product that is observed. And the mechanism on the right is to make the anti-Markovnikov, the less substituted product, and that is not observed. And then on the reaction coordinate diagram, I've put all the intermediates and the reactants and the products. I just haven't put the curved arrows. I'm also not going to write out Markovnikov ever again. So anti-Mark. Excellent. So to make the Markovnikov product, the observed product, the reaction proceeds via a tertiary carbocation. Tertiary carbocations are lower energy intermediates than primary carbocations. Thus, what we see is that to make the tertiary carbocation, there is a much lower activation barrier because the intermediate is lower energy, the transition state is lower energy, and thus there is a much lower activation barrier. So that's to make the tertiary carbocation. And we know lower activation barrier, faster rate. And it's so fast compared to the primary that the primary is not observed. So there's a much faster rate to make the tertiary alkyl halide, and so we don't even observe the primary. It's too slow. Primary carbocations are too high energy. Excellent. So carbocations are involved in these reactions, and so we have to keep in mind everything we know about carbocation stability and how carbocations behave. Let's go ahead and predict the products of this reaction. I see an alkene. I see there are two carbons of the alkene. I see we have HX, so hydrogen and chlorine are going to add across those two carbons of the alkene. Which carbon makes the bond to hydrogen? Yes, carbon 1, the less substituted carbon, and carbon 2, the more substituted carbon, makes the bond to chlorine. So typically students predict the Markovnikov product, the more substituted alkyl halide as the product here. Draw the anti-Markovnikov product so we can just compare. Yes, the anti-Markovnikov product would come from addition of hydrogen to carbon 2 and chlorine to carbon 1. And this is not observed. Everyone can see that this is a primary alkyl halide. So we don't expect it to be observed. Okay. Well, I've got very bad news for you. If you predicted this product, the good news is good job. I wanted you to predict it. But this product is not observed either. So what is going on here? Well, hopefully you are screaming at the screen in a good way because you know what's happening. So let's take a look at the mechanism so we can understand. So it is true that the first step, I'm sorry, I can't draw it like this. Does that bother you too? That really bothered me. All right, HCl. No, you didn't care. Get on with it. Okay, we'll get on with it. So pi CC attacks sigma star HCl. That breaks the HCl bond, generating a bond between one of these carbons. I don't know why I can't write it this way. So carbon 1 and hydrogen, and then carbon 2 will be a carbocation. So we were correct in that we should protonate the less substituted carbon. C1 was protonated to make this secondary carbocation. We did not choose to protonate C2 because that would have generated a less stable primary carbocation. Warning bells, however, should be going off in your head when you hear secondary carbocation, particularly when that secondary carbocation is adjacent to a quaternary carbon. Mystery solved, right? This, before chloride can coordinate, this carbocation immediately undergoes a rearrangement. There's a methyl shift. So the sigma C electrons fill up that empty p orbital on carbon. And this happens, of course, because when that methyl shifts, a secondary, oh, excuse me, not a secondary, a tertiary cation forms. And tertiary cations are more stable than secondary cations. So then from here, certainly, this is an electron-poor species, and it's going to react as you would expect. It will accept electrons with its p orbital, empty p orbital. We're looking for an electron-rich species. Hey, there it is, chloride. Let's rewrite chloride over here. Chloride will attack. That generates this rearranged product. Okay, awesome. So a couple of take-homes. One, carbocation rearrangements can still occur because we're making carbocations. So we need to watch out for that. Number two, good job predicting Markovnikov product here. Good job. But, the most stable intermediates will be formed. And so this unpredicted carbocation shift occurred, and we need to be looking out for that. And so we got a product that was unpredicted, but makes total sense based off of what we know. So we're actually observed this tertiary alkyl halide due to this rearrangement. Want to try again? Yes, you do. So let's predict the products of this reaction and draw a complete curved arrow mechanism. Please force yourself. Stop and try. I'm going to stop too. So pause and try. You didn't fall for my tricks this time, did you? You realize that this alkene looks really similar to this alcohol, which if we treated with HBr would react to form the protonated alcohol. Water is a good leaving group. Water leaves. That generates secondary cation, which ring opens to relieve that wretched ring strain in the four-membered ring and to make this cation. So you recognize that, right? So you knew that we were going to need to consider carbocation rearrangements. So after we have the electrophilic addition step, the alkene adding to sigma star HCl, which breaks the HCl bond and makes a carbon-hydrogen bond. And that carbon-hydrogen bond will be made to one of the two carbons of the alkene. You have to choose. And the bond is made to generate the most stable carbocation. So between the two choices available, protonating at carbon 1 will generate a secondary cation. If you had protonated on carbon 2, a primary cation would have been generated, and that would not be the lowest energy pathway. So we're not protonating C2, protonate C1. All right, I'm not going to mention that anymore. I think you have it down now. So here we've generated a secondary cation, and it is adjacent to this strained four-membered ring. So as we mentioned above, the top of the screen, a carbocation rearrangement will occur. A ring opening, in fact. If you look too hard at this cation, you might realize this could continue to rearrange to continue making more stable cations. We're not gonna go down that pathway. We're just gonna say unless you're given the product and you can tell multiple rearrangements occurred, just do one. I don't want to take you down an endless rabbit hole of rearrangements. So finally, chloride attacks that secondary carbocation by coordination, where the non-bonding electrons attack that empty p orbital on carbon. That gives carbon a complete octet and relieves the formal charge. So we do observe the rearranged alkyl halide that is formed by the most stable carbocation. Let's do it. Oh, this time, what do we see? Well, we see some constitutional isomers of product. If you'd like to pause, go ahead and pause and try yourself. I would love to know how many people actually try themselves. Cool, so let's take a look here. When we think about HBr, HX adding to an alkene, we're typically thinking about the two carbons that were making the double bond. But you can see for the second product that bromine has made a bond to a carbon that was not part of the alkene. So something funny is going on. There's either a mistake, which I know don't want to put past me, but in this case it's not a mistake, it's a rearrangement. So we have this first electrophilic addition step. Again, that breaks the HBr bond to generate the bromide anion. We're going to make a bond to the less substituted carbon to make a carbocation on the more substituted carbon, which for this double bond was carbon 2. Now, we do notice that carbon 2 is a secondary cation and it is adjacent to a tertiary carbon. So we know that this can undergo a hydride shift to generate a tertiary. Now there's two hydrogens here. So to generate a tertiary carbocation, which is more stable. This tertiary cation can react with the bromide that was formed when HBr added to the alkene in a coordination step to form the tertiary alkyl halide. Well, where did the other product come from? Well, it simply came from this alkene. Let me highlight it for you. From this alkene, this product came from the secondary carbocation before it rearranged. So we're just going to rewrite it without the mess. So instead of the rearrangement, it could be trapped by bromide to generate the secondary alkyl halide. Carbocations are a mess, is the bottom line here. And when they can be avoided, you should. On that exciting note, let's summarize hydrohalogenation, the fancy name for HX addition to an alkene. Well, the reactant is an alkene, and we did learn about regiochemistry, so let's show an asymmetric alkene. The reagents are HX, where X can be only chlorine, bromine, and iodine. The product results from addition of those two atoms, H and X, to the two carbons of the alkene. Okay, and you might, it's a little confusing when I draw it like that. I just want to show you that H and X are both added. Now, what are some notes that we might make here? Well, the Markovnikov product is observed, which means that the more substituted alkyl halide is formed because it comes from the more substituted carbocation. Anything else? Yeah, we could think about stereochemistry. Typically for these reactions, we get a mixture of enantiomers or a mixture of diastereomers. And we'll look at some examples towards the end. This particular product is achiral, so it doesn't really apply to it. You may write out it goes by electrophilic addition and then a coordination. You might not. Okay, let's go. Next up, hydration reactions. What do you think could be a hydration reaction to an alkene? What's your guess? What's going to happen to the alkene? Yes, hydration means water, so we're going to add water to it. How exactly are we going to add it? We're going to add it as H and OH. If we just added water itself, then you would have like this crazy thing. So no. We're adding water as HOH across the two carbons of the alkene. Where do you think that the OH will go? Yes, it will go to the more substituted carbon, and hydrogen is going to go to the less substituted carbon if it follows Markovnikov's rule, which this particular reaction that I'm going to show you now will, because it will proceed via carbocations. This will follow Markovnikov's rule. Cool. You think water is just going to add? No, well, it's definitely not. So we're not just going to be able to take the alkene and treat it with water and get a hydration. That's crazy. Water's just not that reactive. Otherwise, we'd be in huge trouble since we are 70% water. What we will need is an acid catalyst. So this is called an acid-catalyzed hydration reaction. So a strong acid is required to make the carbocation intermediate that will then be trapped by water. Excellent. So we have sulfuric acid here. That's an example of one of the strong acids that can be used to generate the carbocations. This time, both carbons of the alkene are exactly the same, so we can protonate either of them. I will choose to protonate carbon 1, carbon 2. Why not? Doesn't matter. They're the same. That generates a tertiary carbocation. Carbocations are electron poor. Their acceptor orbital is the empty p orbital on carbon. So I ask you, are there any nucleophiles? Are there any electron-rich species in solution? Yes, we haven't mentioned it yet. It's water. And remember, this is a hydration, so we're probably going to add water. Yes, it is the electron-rich species. Its donor, or HOMO, is that non-bonding pair of electrons on oxygen. It will coordinate to the carbocation to generate the protonated alcohol. Okay. And obviously we are not going to stop here because this has a pKa of -2. So next we need to deprotonate the alcohol. What base should we use to do that? I hope that you did not say the conjugate base of sulfuric acid. Honestly, I should have never even shown sulfuric acid. That was very bad. I know better. If there's water around and there's sulfuric acid around, the sulfuric acid has protonated water already long before it sees the alkane. So I actually should have shown hydronium. And then that will help you out because water is the conjugate base of hydronium, and water is the best base. Wow, that's awful because water is an awful base. But water is the best base around to do this deprotonation. Do not use the conjugate base of sulfate or sulfuric acid. It is not basic. It is not basic. So use water. Water is basic when you need it to be. When it's reacting with the strong acid, it is a weak base. All right, here we go. So we get this alcohol product. So when an alkene is treated with an acid catalyst in the presence of water, an alcohol is formed. And we have effectively added HOH across those two bonds of the alkene, which is why this is called a hydration reaction. It's called acid catalyzed because what did we do in this last step? We regenerated the acid. So we've addressed this last question. So now I've given you an example of an asymmetric alkene. We will have two different possibilities as to which product is formed. So we can see there's a strong acid and there's water. So that signals to you that you'll be forming an alcohol product, that we will add HOH across those two carbons of the alkene. The real question becomes which atom do you add to which carbon? So what do you think? This is not a trick. This should not be a surprise. Yes, the more electronegative atom, oxygen, it adds to the more substituted carbon. So this tertiary alcohol will be observed. Now, I just applied Markovnikov's rule when I stated that. But, this is because the tertiary alcohol will go by the most stable carbocation. That is how it's formed. Let's draw out the mechanism. So you can pause if you like and draw that out. What's the first step upon treatment with a strong acid? Yeah, protonate something. But in this case, you know that there's an electrophilic addition elementary step. There will be a coordination elementary step. And then for when water is the nucleophile, you'll have a proton transfer step at the end. So let's go ahead and draw the carbocation that results from protonating the less substituted carbon to get the more substituted carbocation. From here, this electron-poor species will react with electron-rich water. In a coordination step, as written at the top of the screen, that generates this protonated alcohol with a pKa of -2. Whoa. So water will act to deprotonate the protonated alcohol, generating the final product and regenerating the acid catalyst. Not so bad, right? You guys can do it. Oh, let's pause and summarize acid-catalyzed hydrations of alkenes. It'd be great if you could try. I gave you an example of how to do the summary. So now you try. Here is what I've come up with. There's an alkene treated with a strong acid catalyst. Now, those possible catalysts, the conjugate bases should not be very nucleophilic. So we want strong acids with non-nucleophilic conjugate bases. So sulfuric acid is a good choice. The organic version of sulfuric acid, tosic acid, that we have discussed before in the context of tosylates, that is an excellent choice. A strong acid we have not discussed yet is called triflic acid. Triflic acid is another sulfonic acid, but it has a trifluoromethyl group instead of this tosyl group, or this, toluene, this aromatic group that tosic acid has. So these are all appropriate acids. You might see them. It really does need to be a strong acid with a non-nucleophilic, probably not a word, but a non-nucleophilic conjugate base. So don't use HCl, don't use HBr, because chloride and bromide are nucleophiles. Cool. This follows Markovnikov's rule. The more substituted alcohol is observed, and this is because it goes by carbocations. So I don't think I mentioned this on the other summary slide, but just keep in mind on your reaction chart that, or wherever you're keeping your notes, you need to be looking out for rearrangements whenever carbocations are around. I'm going to show you two more reactions, but they're basically the same. So this is acid-catalyzed addition of alcohols to alkenes. So we have an alkene, we have a strong acid catalyst, just like we did for the hydration, and then we have an alcohol. And the alcohol here will act in place of water. So everyone, seriously, for reals, pause now and try yourself. Please, please. Last chance. So the strong acid catalyst will immediately generate protonated ethanol, which will protonate the alkene, and it will be protonated on C1 to generate the most stable cation possible, which is this tertiary cation. Now, this is electron poor. It will react with its LUMO, which is the empty p orbital on carbon. We need to look for an electron-rich species. Now, for acid-catalyzed hydration, that electron-rich species is water. But we have replaced water in this reaction with alcohol. So this time the alcohol donates its lone pair to generate this protonated ether intermediate, which will be deprotonated by what? Yes, by, I don't know why I've switched to methanol. I'm sorry, we're in ethanol. It will be deprotonated by another molecule of ethanol to generate an ether functionality. Cool. So by switching water for an alcohol, we generate an ether. And remember, we learned how to synthesize ethers a few classes ago. So this is great. We have another way to make ethers now. Same pattern, right? Electrophilic addition, coordination, proton transfer. Okay, fill out the summary, please. We are almost done. We're just going to switch up the oxygen-based nucleophile one more time. So we changed from water, which generated an alcohol when it reacted with the alkene, to alcohol, which generated the ether when it reacted with the alkene. And now we will look at a carboxylic acid, but it is still an oxygen-based nucleophile. So meaning that oxygen is reacting, and then leave it at that. So we have water, alcohol, And now we're going to look at the carboxylic acid. You know, in each of these cases, there's this proton that we can remove after the attack. Okay, and we still have this strong acid catalyst, and that's because the carboxylic acid is not a strong enough acid to make a carbocation. So let's go ahead and check this out. So the first step is that we'll protonate that will generate for us. So we have electrophilic addition. So I used a protonated carboxylic acid here just to be clear, because I just assumed tosic acid is still stronger than acetic acid, so it probably protonates it first, just like deprotonated ethanol and water first before we reacted with them. All right, then the alkene reacts with that acid to make the more stable tertiary cation. This tertiary cation is electron poor. Okay. And it will react with the only electron-rich species around that's really even remotely nucleophilic, and that is, shockingly, the carboxylic acid. The carboxylic acid is the electron-rich species. It attacks carbon 2. That's kind of hard to see, so I'm going to go around this side here. And that would generate an intermediate that looks like this. And don't worry, I am going to help you kind of see where everything is. All right, so let's say carbon 1, carbon 2. Okay, I made a bond with the carbocation carbon. And then I think you can see where all of this came from. That's from the carboxylic acid. Now, I did not make a mistake here. The carbonyl oxygen, it is the more nucleophilic of the two oxygens, and that is because this intermediate from attack at the carbonyl oxygen, it can be stabilized by delocalization of charge. You can draw a resonance structure that shows this intermediate being stabilized by by spreading that charge on both oxygens. If you had this oxygen, the oxygen of the carboxylic acid attack, you would not be able to draw a resonance structure for the intermediate. Try, you can't do it. So that means it's higher energy, and so that means that, in fact, that oxygen of the OH oxygen of the carboxylic acid does not attack. It is less nucleophilic. It's the carbonyl oxygen. Okay, so we're here now. We're almost to the product. That's certainly quite acidic, so we will just use another molecule of acetic acid to deprotonate. We're running out of room here, huh? And then we get our final product, which is an ester. Cool. So that's the final product here. It's the same series of steps we've been looking at. So electrophilic addition, coordination. Then we have this, I showed you the resonance, delocalization of charge, and then there was a proton transfer to get this cool ester product. This video is getting long, partially because I showed you, 3 different examples of carbocation rearrangements, and I'm really wanting you to get this pattern down. I do have 3 more practice problems. If you want to save them for later, that's fine. You're not going to miss anything. I've taught you everything that you need to know. In fact, we can go ahead and summarize now. We finally learned what happens after the electrophilic addition elementary step between an alkene and some electrophile. This electron-poor carbocation is generated, and it's going to react with an electron-rich species. And exactly what that electron-rich species is can vary, and that will give us different products. So we first learned about HX addition to the 2 carbons of the alkene. This does proceed via the most stable carbocation, forming the most substituted possibility for the product, and that's called the Markovnikov product, the more substituted product. So for example, we did not observe the secondary alkyl halide here. The tertiary alkyl halide was observed. Excellent. We said, okay, well, can you only make alkyl halides by this path? No, you can also make alcohols. And so for alcohols, you had to add a strong acid catalyst, and then you had a water. And so the same order of steps though. So electrophilic addition to generate a carbocation, coordination of a nucleophile, in this case that was water, and then proton transfer. So that was kind of one extra step in comparison to the HX addition that we learned first. And then we just varied the nucleophile. They're going to be oxygen based, but instead of water making an alcohol, we looked at using an alcohol nucleophile to make an ether, and then finally using a carboxylic acid nucleophile to make an ester. So 3 practice problems and then we're done. You want to save them for later? Save them for later. Let's take a look here. I want you, seriously, you have to pause, predict the product, draw the curved arrow mechanism, all of that good stuff. Welcome back. So we have these 2 carbons of the alkene, and let's just label them. So this one is secondary, this one is tertiary. We can see we have a strong acid catalyst and an alcohol. So that tells me the product is going to be an ether. We'll have added H and then OCH3 across those 2 carbons of the alkene. We can go ahead and draw the product, and then we'll just check for any rearrangements or funny business when we write the mechanism. So we know that the nucleophile is going to have added to the tertiary carbon of the alkene. So that was the tertiary carbon of the alkene. That was the secondary. Hydrogen added to that carbon. Good. So we could draw the product. Now let's go ahead, and we've applied the pattern to draw the product. Let's apply the mechanistic pattern just to be sure we didn't miss anything. Okay, so the first step is electrophilic addition. Again, triflic acid immediately protonates methanol when you mix them together, and then protonated methanol acts as the strong acid to protonate the alkene. That does have a pKa of -2. Cool, so the alkene becomes protonated. We protonate at carbon, the secondary carbon, to generate a tertiary carbocation. The carbocation is electron poor, reacting through the p orbital on carbon, which is empty. We look for an electron-rich species. The electron-rich species is the alcohol methanol that is present as the solvent. Methanol will fill up that empty p orbital on carbon with its non-bonding electrons. That attack can happen to the top face of the p orbital or to the bottom face of the p orbital. Attack of methanol to the top face will lead to this protonated alcohol. Attack to the bottom face will lead to us to this protonated alcohol. And of course, the relationship between these 2 protonated alcohols is they are enantiomeric. So you have a racemic mixture of these 2 protonated alcohols, because attack to the top face and the bottom face of that p orbital are equally likely. We drew this out way back at the beginning, about an hour ago, right? Said chloride could attack either face of the p orbital. Same thing here, just different nucleophile. Awesome, we're almost there. So there's a pKa of these protonated ether of about -2. So the alcohol will deprotonate the protonated ether to generate the racemic mixture. And I'm just going to show that proton transfer just for one of the enantiomers for time's sake. All right. Let's take a look at this one. So predict the product and then propose a complete curved arrow mechanism for this transformation. including stereochemistry. An alkene is treated with HX. So there will be an addition of H and Cl across the two carbons of the alkene. Now for this particular alkene, the two carbons of the double bond are exactly the same. So you don't have to worry about which carbon bonds to which atom, hydrogen or chlorine, it doesn't matter. Those carbons are the same. So this is the product, and it will be formed as a racemic mixture of diastereomers. That sounds exciting. Let's look at it. So the first step will involve an electrophilic addition of the pi electrons to sigma star HCl, making a carbon-hydrogen bond and leaving a carbocation on the other carbon. Now, either one of the alkene carbons could have made the carbon-hydrogen bond, and it could happen to either the top face or the bottom face. So here's protonation to the bottom face. Here's protonation to the top face. Now, from here, we have these electron-poor carbocations, and each of them will react with the electron-rich chloride ion here. So it's going to be the nucleophile. Now, for each of these, chloride could attack to the top face or the bottom face, and same for its enantiomer. Chloride could attack to the top face of this carbocation, the p orbital, or to the bottom face. So what have we formed here? Wow, a lot of different things. So we have formed these two molecules, which are enantiomers. And then this is another set of enantiomers, which is diastereomers with the first set. Wow, so that's what I meant by a racemic mixture of diastereomers. Last one. We're going to write this one out together. Propose a complete curved arrow mechanism that explains the formation of this transformation. Please pause if you'd like, and I highly recommend it. So if we just analyze what's going on here, we can see from the outset that a bond was made between carbon 1 and hydrogen, which is not surprising. We expect that to happen, and we would protonate in the first step and generate the more stable carbocation. What is weird is the fact that this carbon-oxygen bond was formed at carbon 3 and not at carbon 2. And that tells me that this carbocation was involved. So we're going to keep that in mind while we're continuing on with the mechanism. One more thing to point out here, you notice that this benzene ring, this aromatic ring, it does not react. So aromatic rings are unreactive to these electrophilic addition reactions. You'll learn more about how to encourage or facilitate reactions of aromatic rings in the next course. But in this course, don't do anything to them. They don't react. The first step, electrophilic addition. That generates a secondary carbocation. Now, really not very many bells and whistles pop out about why in the world there's going to be a rearrangement here. But you might notice that there is just this one carbon in between the carbocation and the benzene ring. And if there were a hydride shift to occur, that would generate the carbocation that we've been expecting to form. Look up at the top of the screen. This is the carbocation that we've been expecting to form. So that carbocation is formed because it can be stabilized, or it is stabilized by delocalization of charge. So you could imagine several resonance structures that you could draw to show how this molecule is stabilized by delocalization of charge. Thus, this carbocation rearrangement does occur, the hydride shift does occur, because we end up generating a more stabilized delocalized cation. Sharing electrons lowers their energy and stabilizes the charge. Awesome. So now we get the carbocation that is formed, and this just reacts the way that they did in every other example that we examined today. Water will act as the electron-rich nucleophilic species, donating its lone pair of electrons in a coordination step to generate this protonated alcohol. The protonated alcohol, it then undergoes proton transfer using water as the base to regenerate the acid catalyst, yippee, that's the definition of a catalyst, and the observed product. So you guys have it. You've got it. That was a tough one. I already summarized. Now you need to stop and summarize yourself and go practice.